Good morning, everyone. It's my great honor and pleasure to be here and share with you the recent works we have been done in the past few years. Today, I'm going to focus on fuel cell application, and I will talk about a little bit background about how it works, and then we will talk about the strategy when we develop the membrane electrolyte for the fuel cells. And then finally, I will focus on today's topic on how we use Electrospun polymer nanofibers as a strong ionic conductor. This is my research focuses. Actually, we develop various application. Basically, we develop frontier materials. We apply them in energy, including solar cells, fuel cells, and lithium-air battery. We also develop some material for water treatment, especially thin-film composite membranes for water desalination. And we also have nanomaterials, especially thermal-responsive nanoparticles for drug control release. And today I'm going to focus on the energy field. And today we will talk more about fuel cells. This is the working principle of a typical fuel cell. The left-hand side uses hydrogen as the fuel, and this is very common and most commercially developed product and the most mature technology so far. And you can see the overall reaction is like combustion of hydrogen, and the product is water. Theoretically, it can release 1.2 volts, basic on Gibbs free energy estimates. The drawback with this system is the hydrogen is very explosive gas. And in addition to improve to have a pure hydrogen supply to the system, it has a very complex system, and it requires a lot of footprints, including hydrogen generation, hydrogen purification, and so on. So we look at another different type of fuel cell. Here we use ethanol as the direct fuel. So that is a liquid type of fuel, similar to gasoline when you fill your car. And it's also a complete oxidation reaction. The theoretical energy release in this direct methanol fuel cell is 1.21 volts, which is similar to the hydrogen fuel. The limitation in this type of methanol fuel cell is that if we adopt the conventional materials from the hydrogen fuel cells, the current benchmark membrane is Nephion from DuPont company. And Nephion membrane has very high methanol crossover. That means the fuel at the anode will be diffused into the cathode. And when that happens, first of all, you will have a fuel loss. And secondly, the methanol will also react at the cathode and reduce and also cause another oxidation cell potential. And therefore, the overall cell potential you can obtain is much lower than the theoretical value. And also, in this system, we have to use high loading of platinum-based catalyst. That is the most costly ingredient in the fuel cell assembly. And also, the Nephion exchange membrane is costly. But for this system, if you compare the energy released by these two systems, you can see that per unit volume of the fuel, you can have almost 40 or 50% higher density, energy density compared with the hydrogen fuel. So it still has some advantages, especially for the some applications such as transportation, like this is a DMFC, they stand for direct methanol fuel cell, the fuel cell car, fuel cell scooter. It's also convenient to use them as a power bank or electricity generators. So basically, the advantage of the DMFC is that it can be used in portable systems. And today, I'm going to talk about the hydroxide conducting mode of direct methanol fuel cell. The half reaction of the anode part is that we will have hydroxide ions in conjunction with the fuel into the anode part. And therefore, you will release 6 electrons out of it. The electron will travel along the external circuits and reach cathode. At the cathode, we will supply humidifier oxygen into it, and it will contain, it will release, let me see, I think this is not very powerful. Okay, I will try to use the pointer. The cathode side, we will combine the external electron circuits, and then hydroxide ions are generated. Now, this design is a little bit different from the previous, which we used a proton exchange membrane. Here we use hydroxide conducting membrane for this application. And the advantage is that the methanol oxidation reaction rates is much faster in the alkaline media than acidic environment. And secondly, for this oxygen reduction reaction, there are many other catalysts available, especially for less expensive non-platinum-based catalysts. And from the scheme, you can see that the hydroxide ions are generated at cathode and diffuse into anode compartment. And therefore, the direction of hydroxide ions is opposite to the methanol permeability direction. And therefore, they will suppress the methanol crossover. And lastly, it is easy for water management, especially the water is produced now at the anode side and is in aqueous solution. So it's very easy to manage compared with the proton exchange membrane, where water is generated at the cathode, and cathode flooding usually a major concern in the commercial application. Now, the challenges for this kind of electrolyte membranes are we have to develop the membrane with very high ionic conductivity, but it cannot be electron conductors. Otherwise, the electron will go through the membrane and cause electrical shock current. And secondly, of course, we need to have very low methanol permeability. So the methanol crossover is not a big issue in here. So in order to develop the high ionic conductivity membrane, we have several mechanisms that we have to understand before we can set up our approaches. For any small molecules to go through a polymeric film, usually there are several mechanisms where it can go through it can transport from upstream to the downstream side. The first thing is called vehicular diffusion. In this diffusion part, basically, the small permeance is taking the route through polymeric free volumes. The free volume is very small moving space between the polymer chains, and usually the moving rate is in femta or picoseconds. So it's a void, but it moves very fast. And this is the part where small penetrants can go through the polymer film. And that is also the property that will give the polymer the elasticity and plastic properties. So this is the first and most common one of diffusion. And the second is called hopping mechanism. This is especially important with some fixed charge functional groups, such as cation and anion exchange membranes, where we have fixed charges and the ions just jump from one functional group to next and then go through the downstream side. The last one is called surface diffusion. And in this composite, usually we have some small long-range channels. So it's like a super highway for ions to go through from one side to the other. And this is very common when we look at carbon nanotube composite. So in the past, we have developed many different kinds of membrane electrolytes using these different approaches. For instance, we can add nanoparticles into polyvinyl alcohol. The polyvinyl alcohol is a semi-crystalline polymer. When we add the nanoparticle into the polymer matrix, it will interrupt with the polymer chain alignment and disrupt the crystalline region. And therefore, we will have less crystalline region, more amorphous, and more free volume for ions and small molecules to go through. The second approach is to combine carbon nanotube, but here usually we have to graft the surface of the carbon nanotube with the host polymer matrix. Therefore, we can increase the compatibility between these two components when we make into the composites. And secondly, it also provides the insulation layer, so it will not be electron conductor after we make this composite. And the third approach is to graft some nanoparticle into it. So it's kind of the combination of these two approaches. And all of this can have very high conductivity compared to the single polymer materials. And recently we focused on we focus on graphene oxide. We use it as a barrier layer, so it can suppress the methanol crossover. And we also published recently a paper regarding to incorporated some nanoparticles. These are also functionalized with tertiary amine functional groups. And therefore, we will combine the hopping mechanism, vehicular diffusion, and other mechanisms together to enhance the ionic conductivity. And today I'm going to talk about electron-spun nanofibers. When we start with this approach, we look at literature and see what has been done so far. We know that some groups reported that methanol permeability is reduced, which is positive in our application. And some group also found that there will be higher conductivity achieved using this nanofiller. And additionally, some group have published that this composite Nefion and Nefion nanofiber will have this performance using the methanol fuel cell. And we also look at the different possible conduction mechanism if we apply electron-spun nanofibers into our composite. We thought there may be some positive mechanism, such as the surface diffusion, which is similar to the surface along the carbon nanotube, or the anisotropic aggregation of the ionic clusters, or the surface where the softening functional groups will be aggregated and provide some hopping mechanism for proton. And we look at those and then start to define our objective. So here we try to prepare quaternized polyvinyl alcohol electron-spun nanofibers. We put them and mix into composite with the same molecule, same polymer. We characterize the nanofiber mat and the composite. We try to correlate the cell performance with the membrane characteristics. And also, we want to understand what makes the ion conduction work in this system. This is the schematic how we synthesize our polymer. We start with polyvinyl alcohol. We use this chemical to introduce the tertiary amine functional groups into it. So this is our quaternized polyvinyl alcohol chemical structure. And the powder will be a little bit brown color because after amination, the color will become darker usually. And then we put this polymer into our syringe, and we use the electron spinning equipment. Here we have a high voltage along the collecting plate and the needle side. Therefore, it generates high power of voltage and withdraw the solution and collapse on the collecting plate. And therefore, we can form a very porous structure using this electron spinning technique. And then we put this in a mold and we fill some QPVA polymer solution into it and then dry, then we will have some composite. And actually it has the nanofiber structure and the polymer dense film structure. And then we make them into a single cell. And the membrane is located in the middle part. On the two sides of the membrane, we also have anode and cathode, which we use catalysts on carbon cloth. And those serve as the accelerator for the reaction, so we can collect the currents in a faster way. We also have some gasket and flow field to surround this MEA, and then we make into a single cell. And then we have a potential state to measure the electricity and voltage generated by changing the current or voltage. And therefore, we can determine the cell performance. So let's begin with the characterization of the QPVA Electrospun nanofiber mat. This is how it looks. It looks like Teflon tape or something. It's very light color, pale off-white color. And if we look at under microscope, you can see there are lots of pores. They are interconnected. The porosity is 71%, and the pore size about 200 nanometers. And if you look at the fiber, it's less than 100 nanometer in diameter. So it is a nanofiber type and very porous structure. Then we measure this. We just took this nanofiber mat and used XRD to see the crystallinity structure. And very surprisingly, the fiber mat have very low crystallinity compared with the pristine QPVA. So these have drawn to our attention that there is something happened during the electron spinning process. And we also measure the conductivity of the fiber mat. The conductivity is at least 2 times higher than the original polymer. So we think maybe the crystallinity changes and the conductivity increase, because when we have less crystallinity, the amorphous region is helpful for the ion conduction and the ion transport. Then we make this to further examination. We test the tree density and the frictional free volume, and then you can see that the polymer free volume is increased at least 2 times to 3 times. And we also use DSC to measure the crystalline melting enthalpy, and you can see the peak is gradually reduced. So that means the crystalline region has been interrupted. Okay, and we also calculate the polymer crystallinity. It increased from almost 10% to 6%. So the crystallinity has been modified significantly. So we want to further understand what's going on with the nanofibers. Then we use the uranyl acetate to stain the nanofiber, because our thinking was that if there are some region that is more amorphous, this region is more easy to uptake the water and the stain, so it will become much darker under the TEM. And this is how we got. You can see the inner part is darker, so that means this part is more amorphous, and it's more soft in the core. And the shell side, you can see it's not much affected, so we kind of have some conclusion that it has a core shell structure. The core is soft, like spring roll or burrito, it's more loosely packed, where the outer surface is more crystalline. And therefore, there are different regions, and different regions will have different functionality, especially in the fuel cell application. So here we can conclude that crystallinity decrease, also the polymer density decrease, however, the free running increase. And this mainly happen in the core region of the nanofibers. The morphology looks like this. The top surface of the composite membrane is very dense. You do not see any holes. And these are the Electrospun fibers part. And the other polymer kind of fill the voids in a nanofiber and also a little bit above it. So we will have this composite membrane. And we calculate by the weight ratio, we found out that the nanofiber accounted for 6% in the overall composite. We also measure methanol permeability, and we find that the composite has much lower permeability. Methanol permeability. Again, that is a positive side on our application. And we also measure ionic conductivity. You can see the conductivity increase, and we believe that the ionic conductivity increase is related to the soft inner core that provide an ionic conducting path. So the schematic would look like this. The soft core allows ions to go through, where the hot shell is a methanol barrier. So when we have this composite, we found out it has much higher conductivity while lost less methanol permeability. And the conduction of the ions is different from the carbon nanotube. In the carbon nanotube, it's along the surface to diffuse. However, in the Electrospun nanofibers, basically it takes the route in the inner core. The cell performance look good compared with the original polymer, and also during long-term tests, it can stand more than 250 hours and above. So we can see that the cell performance was increased by the nanofiber, and also it is very durable in a fuel cell test. So in conclusion, we have prepared superconductive coaxial QPVA nanofibers, and these nanofibers are prepared by electron spinning method. The QPVA composite can suppress methanol permeability due to the hard shell structure. And the core exhibit amorphous region and form super ion conductive path. And finally, we validate that it's an effective electrolyte, especially in the alkaline fuel cell. And with that, I would like to acknowledge the funding agency and my collaborator and my students. And finally, thank you very much for your kind attention.
Thank you very much, Doctor.
Thank you very much.
Questions? Here we go.
It's very interesting lecture. Did you test for the cells, like biocompatibility and drug delivery system with this?
You mean the biocompatible?
Yeah, this polymer.
At this stage, we haven't tested. But in the future, we are going to have some collaboration with other group in Europe, and under that project, one of the scope is to test the safety and biocompatibility of these composite membranes.
So your future research is towards drug delivery, right?
Yeah.
Okay. Thank you.
So your polymer looks like what soluble if it's not cross-linked? Is it cross-linked?
Yes.
And then how do you, I'm curious about this, how do you specifically spin this, make this fiber? So you dissolve your polymer in certain solvent?
Yes. It's in polymer solvent. Usually from 10 to 20% polymer solution. Then you put them in syringe. So, but before at this stage, it's not cross-linked. Usually, we only cross-link when we make the membrane, when it has formed a film. Then we may dip, or we may not dip in glutaraldehyde solution. Usually there's a post cross-linking.
Okay.
Yeah.
Okay. Got
But-
it. So.
Yeah, but the data here I presented are not cross-linked.
Okay. But
Yeah.
if it's not cross-linked, then I guess it will be more soluble when you put it into an electrolyte solution where you're matte.
Yeah,
Lot of
you're
soda
right.
where you want?
You're right. If it's not doped with potassium hydroxide, here actually, after we make the film, we dip them in KOH solution. And the KOH will have some kind of cross-linking effect on it, so they maintain the stability of the film.
Okay. Thanks.
One question. How about the lifetime of the membrane you made compared to the lifetime of the membrane right now, the PEM membrane right now in hydrogen fuel cell? Do you have any test result for that?
So far, we test up to 300 hours or so. And usually in this time, there are something happen usually. First of all is that we put the recycle of the fuel into the system. And therefore, the effective concentration and the conductivity of the solution actually decrease gradually. So they will have a little bit effect on our cell voltage. So usually if you see a slow decay of the voltage here, usually that is due to the decreased methanol concentration. And I believe that if we can somehow replenish the feed solution, they will minimize some of the thing. But yeah, we also do fountain test, and fountain test seems it's very durable.
Thank you. You
mean how to measure crystallinity?
Yeah.
Usually we have two ways to check. First of all, is to look at XRD and to see the intensity of it. But the more quantitative method is to use differential scanning calorimetry. Because for this semi-crystalline polymer, you can see a crystal peak. And if the peak enthalpy decreased, then you know the crystallinity has been decreased. Yeah, so that is two ways to check.
So this TM shows any crystal pattern?
Here, we do not use other technique to check. I think one way will be to use more like a small angle X-ray. But then the hard part is that we have to focus either on the inner wall or on the outside shell. So that also requires high magnification of the microscope.
Yeah.
Otherwise, you will only get a bulk property, not individual points.
Yeah.
I think that's the challenge.
Okay, thank you.